Okay, so this is the example 17.3. I think it's going to be easier just to work these individually. That way I can upload them pretty quick. So let's read through the problem. So example 17.3, the decomposition, and that's key there, of PCl5 was studied at another temperature. So another temperature meaning that the one that we calculated in 17.2 or 17.2 would no longer be valid, the equilibrium constant, because remember they change at different temperatures. So 1 mole of PCl5 was introduced into an evacuated 1 liter container. The system was allowed to reach equilibrium at the new temp. At equilibrium, okay, and this is key, 0.60 moles of PCl3 was present in the container. Calculate the equilibrium constant at this temperature. Okay, so here we're going to need a couple of things. Our first thing is we need a working reaction. So PCl5, okay, yields PCl3 plus Cl2. And we already know that this is balanced. We're going to set up the Rice table that we learned a couple of units ago. Sorry. And we're going to perform a Rice calculation. Okay, so initially, our problem said that we started out with 1 mole of PCl5 in 1 liter of the container. So that's going to be a 1 molar solution. Initially, we start out with 0 of this and 0 of this. Now it says at equilibrium, so at the E down here, 0.6 moles, okay, of PCl3. Now since this was in a 1 liter container, we know the concentration of this is 0.6 molar. Okay, so we need to fill in all the other ones. This is where you have to go back and look at your stoichiometric amounts. This is a 1 to 1 to 1. And so if at equilibrium, this is how much 0.6 was formed. Okay, that means 0.6 of Cl2 was also formed. Okay, we need to know how much PCl5 was used. Well, once again, since this is a 1 to 1 to 1, we know that we used 0.6 molar of that. And so at equilibrium, how much PCl5 do we have left over? Well, you do the subtraction, so it's 0.4. And now that you have your equilibrium concentrations, you can plug it in to your equilibrium expression, which is going to be the same. Okay, so Kc, the concentration of our product, so 0.6 times 0.6 divided by our concentration of our reactants, so 0.4. And our Kc for this one is going to be 0.90. Okay, and this is different than the previous problem because this was at another temperature. Okay, but let's go back and look at those Rice tables. We're going to do one here that has different coefficients in front, but a lot of this is pretty straightforward. So let's stop the video.